One of the most fascinating aspects of Quicksort is its runtime. So it turns out that the runtime depends critically on where our pivot ends up. And so the best possible situation is that the pivot always lands in the middle. Now, if it's not obvious why that's the best case, it will be soon. So let's just start by trying to understand the runtime of this best case that I'm claiming. So if the pivot always lands in the middle, then we end up with two subproblems that are about half the size of the original problem. Slightly less. Now, if each of these two new pivots also end up in the middle of their respective subproblems, we end up with four subproblems of roughly n over 4 in size. Those, in turn, could potentially end up exactly in the middle. And so this is a rough cartoon of what the best case looks like. Now, at this point, there's only size 1 problem, so we're totally done. And so now we ask ourselves, what is the best case runtime? So I'm going to let you think about this a little. See what you come up with, and then I'll spoil it for you. Now, one thing I want you to focus on is the total amount of work at each level. Okay, so with that hint, perhaps, hopefully you saw, that at the top level we did one partition on the entire array, which took around n time. Okay, so I'm just doing this as a rough estimate thing. It's theta n. Okay. At the next level, well, we have two halves that both do, we have two partition operations that are both about n over 2 work. And so in total, we could say, well, it's about n over 2 arbitrary units of time plus another n over 2 arbitrary units of time, so it's about n. Now, yes, technically speaking, it's one less, but that's pretty small compared to n. Okay, so at the next level, we have n over 4. There's 4 such problems of around n over 4 in size. So the overall amount is about n. And that goes all the way down to the bottom. So the overall runtime then is just going to be n, because it's n work at each level, times h, where h is theta log n. What's h, by the way? Well, that's the number of times that you run, the number of levels, so to speak. So overall, the runtime is theta n log n in the best case. Okay. Also, this interesting thing happened. You'll notice this n here. It's a little wiggly. There's some new thing going on with Google Slides where it's rendering in a new cool way that sometimes causes glitches. Not important. All right. So that's the best case. And actually, you'll notice that it looks awfully like our merge sort runtime. How about the worst case? Well, the worst case, and again, I'm just claiming this, is that the pivot lands always at the beginning of the array. So first, I want you to give me an array that actually does show this pattern shown to the right, where the pivot always ends up in the same location. And then second, tell me what the runtime is. Okay, so an example would be an array that's in increasing order, like 1, 2, 3, 4, 5, 6. If you quicksort this using the algorithm we described in class, then you will get the pivot, which never moves, and we keep having a subproblem on the right. And each of these partition operations takes n time, where n is the number of items remaining. And so the overall runtime would just be 1 plus 2 plus 3 plus 4 all the way to n. 1 plus 2 plus 3 plus 4 all the way up to n. And so the overall runtime would be theta n squared. And so what we have is that in the best case, our algorithm is n log n, but in the worst case, it's n squared. Now compare that to merge sort, which is n log n in both cases, and you end up with a situation where it seems like, well, quicksort doesn't seem very good. Nonetheless, quicksort empirically, if you just run it on random data, it is often, not always, but often the fastest sort. And so the question is, how is that possible? How is it that an algorithm that is occasionally n squared could ever be the fastest, considering that we said that the difference between an n log n algorithm and an n squared algorithm is basically game changing, right? It's a totally gigantic deal, the biggest possible deal, changing orders of growth. And yet here I'm saying, well, yeah, it's n squared in the worst case, but it's actually better overall. So how does this work? Well, in the next video, what we'll do is we'll do a couple of little proofs that demonstrate that even despite this fact, it's actually not something that we need to be totally worried about. That it, on average, as long as we don't have worst case data, it's going to be an n log n sort on average. Okay, so that'll be in our next coming video.